Okay. Yeah. Good morning, all. So let me start off with presenting the screen. Yeah. Is the screen visible to you?
Yes, sir.
Okay. So yeah, let us have a quick recap of what we discussed in the previous class. So we discussed about the Bayes theorem. What is Bayes theorem? And we defined the formula, uh, the different notations in the formula. P of h, that is initial probability or prior probability, and P of d, which is the probability on the training data d, right? Then P of h given d, that is probability of observing data d given the hypothesis h, right? And then probability of h given d, which is the posterior probability, that is we are going to compute using the above three notations, right? So P of h given d is called the posterior probability. Yeah, we saw an example of H map, the formula for H map, that is the maximum of posteriori hypothesis. How can we get a maximum of posteriori hypothesis? What we saw. And in case when there is no single maximum of posteriori hypothesis, then we have to consider the maximum likelihood hypothesis, right? So in case if there are two or more maximum of posteriori hypothesis, right? So that in that situation it becomes difficult to point one single maximum of posteriori hypothesis. So in that case, when we have multiple maximum a posteriori hypothesis, we consider, instead of map, we consider ML, that is maximum likelihood, right? So HML and the formula for that. We saw example also with respect to the HMAP and HML for the detection of a cancer disease in a patient, the probability of having a cancer given a set of population, then probability of not having a cancer, probability of testing positive for the patients having cancer, and then for probability of testing negative for the patients who are having cancer, then probability of testing positive for not having cancer, and probability of testing negative for not having cancer, right? So we saw these situations, and we raise a question whether should we go for diagnosis, or whether we diagnose the patient as having the cancer or not, let's say when the lab result is positive. So in that case we saw an example also, computing the probability of having the cancer, right, and is tested positive. So that is 0.21, which is roughly 21 percentage. And then at the end we discussed four rules, that is a few fundamental, basic probability formulas, that is product rule, sum rule, Bayes theorem itself, and the theorem of total probability. So these two you must have already aware, product rule and sum rule, but Bayes theorem and the theorem of total probability is what is new to you, and these are the two formulas which will be further using to, for various derivations and understanding problems. So with this, let's start off with today's lecture. That is, our topic of discussion will be Bayes theorem and concept learning. Right? We have already seen what is basic Bayes theorem, right? What is a Bayes theorem? So now in this today's lecture, we'll be dealing with concept learning in Bayes theorem. So for that, we have two topics, that is brute force based concept learning and map hypothesis and consistent learners. Right? MAP stands for, by now you should be aware, MAP is maximum a posteriori hypothesis. So these are the two core concepts of Bayes theorem and concept learning. Brute force, which we have already seen, I think, in module 2, what is a brute force method, right? But here we are going to be focusing upon a brute force based concept learning, and also maximum or posteriori hypothesis and consistent learners, right? How can we say that there are different types of learner and which learners are consistent learners? So we will have a look upon these. So starting off with brute force based concept learning. So brute force, before discussing the concept, right, we have to understand how does the algorithm works, what is the algorithm all about, right? So brute force map learning algorithm is what is in front of you. Simple, two steps, that is to compute first the posterior probability and then output the most highest posterior probability. That's it. These are the two simple steps in the brute force map learning algorithm. What we do is for each hypothesis, for instance, let's say a hypothesis small h, in the set of all hypotheses, that is capital H, right? We calculate the probability, posterior probability for all those hypotheses, right? For each hypothesis. So for every individual hypothesis, we now have the calculated posterior probability, right? Posterior probability, by now you should be aware what is a posterior probability, right? So if the formula is right in front of you, that is P of H given D is what we are going to compute. This is from the Bayes theorem itself, right? This was the Bayes theorem that P of H given D is equal to P of D given H multiplied by P of H and whole divided by P of D. That is probability of the data, training data. Right. So once we compute the posterior probability for each of the hypotheses in the set of hypotheses, now we are in position to have the posterior probability of every individual hypothesis, right? In the set of hypotheses. Now, among this set of calculated posterior probability that we have for each hypothesis, we are going to output the maximum, or you can say highest, posterior probability, right? And how do we compute that? We have already seen the formula for that. That is H map. H map is hypothesis for the maximum posteriori hypothesis. And for that, the formula is H map is equal to R max P of H given T. Right. So we have already seen the derivation, or you can say the how did we land up with this formula? Let me take you back to that slide. Yeah. So this was the formula that we ultimately end up. That is H map is equal to the R max H belonging to H, that is small h, that is instance of an hypothesis belonging to the set of hypothesis capital H, probability of H given T, right? So with this we can get to know the maximum or the highest posterior probability, right? So once we have this maximum posterior probability or the highest posterior probability, then we move ahead to discuss the concept learning in the base in the brute force method, right? So for that we need to have some assumptions. There are some standard assumptions which are considered for this concept learning in the brute force based method. So the assumptions are: number one is training data, which is the D, is noise free. Right? We assume that the set of training data that we have is a noise free data. We don't have any noise. Unlike candidate elimination algorithm and even ID3 algorithm, we those algorithms were robust enough to handle the noisy or erroneous data. Right. But here in the Bayes theorem, in the brute force map hypothesis algorithm, we are going to assume that the data that we have, the data that we are going to give as input, is a noise-free data. Right? Right. So when we say that it's a noise-free, in other words, it is like the data for any instance. Let's say di, small letter d indicates a particular training example or training data from the set of training data capital D. So T is nothing but it actually belongs to the capital D, right? So Di is one instance of, let's say, capital D. So the assumption here is that Di is equal to C of Xi, that is target concept, right? C is nothing but the target concept C of Xi. So if I have to put it in simple words, this means that the every training data, right, every instance of the training data capital D should be consistent with the target concept C for any instance Xi, right? So then we can say that the data is noisy free because it is consistent with the data, right? It doesn't have any noise or erroneous data. So that is one assumption that we consider for this method. The second assumption is the target concept C is contained in the hypothesis, right? So we are simply assuming that whatever the output that we are expecting, that the output that we are targeting, is present in the hypothesis space, right? Hypothesis space is nothing but the collection of hypotheses that we have, and out of which one hypothesis will be our target concept. So this is one assumption, that from the set of the hypothesis, we are going to have one hypothesis which is actually our target, right? The target concept C. So, but there can be probability that the target concept that we are targeting may not be present in the hypothesis space. That is one probability, right? But as a matter of point here in this method, that is in brute force map learning. So the concept learning algorithm, this assumes here, it simply assumes that whatever the target concept we are targeting is present in the hypothesis space, right? Is contained in the hypothesis space, right? So that is the second assumption. Third is that we have no a priori reason to believe that any hypothesis is more probable than any other, right? So we are assuming here again that we don't have a priori reason, right? A priori reason for what? A priori reason to believe that any hypothesis is more probable than any other, right? So whenever we encounter a hypothesis, we simply assume that there is no more probable hypothesis than any other hypothesis. So this is an assumption that again we are making. So when we have these assumptions before we start process, only then we can proceed ahead to understand this Bayes theorem, the brute force Bayes theorem. Uh, but depending on these assumptions, for the assumptions that we have just considered, these three assumptions, when we have these given assumptions, we tend to ask this question. Next question that arises is that what values should we specify for this P of H and P of D, right? Because there are a lot of assumptions that we are making, right? There are three assumptions that we have assumed. The number one is noisy free data. Let me show you the assumptions again. The data should be noisy free, right? That is one assumption. The target concept is contained in the hypothesis. This is the second assumption that we are making. And third is there is no a priori reason, right? A priori is nothing but there is something which has been observed by theoretical means, right? Only on theoretical basis and not on practical. So we have no a priori reason, that is no theoretical reason to believe that any hypothesis is more probable than any other hypothesis, right? So these are three assumptions, but when we consider these assumptions, the question arises is then what is the value that we have to consider for P of H and P of D given H, right? So P of H is simply the ratio of 1 is to the hypothesis space, right? The absolute value of the hypothesis space, that is capital H. So that becomes our probability of the hypothesis, which is nothing but, can anybody tell me what is this P of H now? Yeah, anybody who can say that what is this P of H? The probability of hypothesis H. What is this? Or in other words, what it is called? Anybody? Yeah, anybody would like to answer that? What is probability? Let me show you the slide again. What is P of H? We have already defined this notation. What do we mean by P of H? Yeah, Aditya.
Yes, sir.
What do we mean by P of H? We have already defined this notation, right?
Yes, sir.
So what is the other name, or you can say in other words, what do we call P of H? What do we mean by P of H? That is probability of the hypothesis. What is this probability called?
So prior probability
Yes.
of it.
Good, Disha. So P of H is the prior probability, or also we sometimes term it as initial probability, because this is the probability which we are computing before we process, right? Before we compute the actual probability considering each hypothesis, right? So before we compute the probability considering each hypothesis, whatever the prior knowledge we have discussed in our introductory class, the one of the key aspect of this Bayesian learning is the prior knowledge. Right? We need to have some prior knowledge. That is one difficulty with the you can say Bayesian learning, is that we need to have some prior data, prior information, or the prior knowledge. Only then we can proceed ahead to find the probability. So the prior knowledge in terms of the prior probability is what we have. So how do we compute that prior probability? Is P of H, and which is also called as initial probability, because this is something we are getting values we are getting initially, and then using these values we are going to compute the processed or the calculated probability, which is also called posterior probability, right? And the posterior probability is notified as P of H given D, right? So this is the posterior probability, also called the Bayes theorem, right? So yeah, anyway, so when we have these given assumptions, right, under these given assumptions it becomes little difficult to define or specify these two notations, that is P of H and P of D given H, right? So P of H is defined as the ratio of 1 is to the virgin space, the hypothesis space, right, the absolute value of the hypothesis space H itself, right, for all the hypotheses in the set H. So that's how we are going to use the value of P of H. And then similarly, P of D given H, that is probability of the data, observed data, given the hypothesis H, we are going to get that value as 1 if the instance, all the training data instance is consistent with the hypothesis instances, right? For all those instances present in the training data set D. If they are not consistent, then it will be 0. Probability of the D given H will be 0. So how do we get this 1 and 0 here? In simple terms, if I have to mention, the probability of D given H will be 1 if the data is consistent, and otherwise, when that is when the data is not consistent, the probability will be 0. Right? So let us understand two cases. I think just a minute. Some people are still willing to join. Latecomers. Okay. So with this understanding of the assumptions as well as the specification of these new notations, P of H and P of D given H, let us consider two cases wherein we have inconsistent data and consistent data. Right. So let's say we have a case here where hypothesis H is inconsistent with the training data. Right. So we have a single instance of an hypothesis from the set of hypothesis capital H, which is not consistent with the training data D, right? So in that case, as you must have already made it out from the previous uh, formula here, that when the data is inconsistent, the probability of D given H becomes 0, right? So in that case, we substitute the formula, the value of P of D of H, D given H, that is the formula, this is actually from the Bayes theorem, right? If you can recall from the Bayes theorem is P of H given D is equal to P of D given H multiplied by P of H divided by the P of D, right? So this ratio, this particular formula is very important. You have to remember this formula throughout this module. We'll be using it numerous times. So in this formula, as the hypothesis H is inconsistent with the training data, our P of T given H, this particular value becomes 0, right? So this value is 0, and when we multiply this whole thing from 0, so the ultimate answer that we get is 0 itself, right? So when we, if I have to put it into a nutshell, that when I have the hypothesis which is inconsistent with the training data, then my posterior probability, right? This is my posterior probability, right, or the computed probability. Please remember, this is our posterior probability. Anyways, so P of H given D is the posterior probability, and when we have an hypothesis H which is inconsistent with the training data, then the posterior probability also becomes 0, right? And we can say that the posterior probability of the hypothesis is also inconsistent with the training data D, that is, it is 0. Now let us have a case where the hypothesis is consistent with the training data, right? So again, you recall the formula, that is this formula itself, the Bayesian Bayes theorem formula. So when we have the data, the hypothesis which is consistent with the training data, then we substitute the value of P of D given H here as 1, right? So this will be now 1. Earlier it was 0, now it will be 1, right? Because it is consistent. Here it was inconsistent. So when it is consistent, the value of P of D given H is 1, and probability of H, as we have assumed, hope you remember the assumptions that we have taken, the probability of H, right, is the ratio of the vergence hypothesis space that we have by 1, right? So this will be this is the assumption, because of the assumptions, the definition that we have formed for P of H, the formula for the P of H is 1 divided by the absolute value of the hypothesis space H, right? So that is replaced with the value here, the form in the formula here. So when we compute the ultimate answer for the posterior probability that we get is the ratio of the vergence space itself, right? The ratio of 1 is to the vergence, the absolute value of the vergence space. Vergence space for the hypothesis from H, that is the set of hypotheses that are consistent with the training data D, right? Which is nothing but V of VSHD here is actually the vergence space of H with respect to D, right? And then we can say that hypothesis H is consistent with the training data D, right? So these are the two cases wherein we saw how we end up having the value of posterior probability, right? When the hypothesis is consistent and when the hypothesis is inconsistent, right? So when the hypothesis is inconsistent, it is quite clear that the posterior probability is also 0. But when the hypothesis is consistent, the value of the posterior probability is the ratio of 1 is to the vergence space of H with respect to D. Right. So for understanding, you must have this question, sir. P of D. How do we have P of D as this value, right? How do we come up with this value? This P of D is substituted with this ratio of vergence space and the hypothesis space, right? So this derivation is what we are going to see now. That is the derivation for the probability of the data D from the theory, theorem of the total probability, right? Hope you remember the fundamental probability formulas that we saw, right? So basic probability formulas. Let me show you that table again. Yeah, so this particular formula here, theorem of total probability, right, wherein for all event, that is if event a1 to an, we have these many numbers of event are mutually exclusive, right? When these events are mutually exclusive, then we sum up the probability of all these events, right? We sum up that the probability of all the events is equal to 1. So this formula here becomes very important for us to derive that probability of training data, that is t, right? So when we consider this formula for the theorem of total probability, let me go back to the current slide. Yeah, so we have that formula here, that is the theorem of total probability, and which says that the hypotheses are mutually exclusive. What do we mean by mutually exclusive? Mutually exclusive is for all the instances I, right, which are not equal to j, right? For all the I which are not equal to j, the conjunction of the probability of hi and probability of hj, right, will be 0. It is equal to 0. So when we substitute all these values, that is probability of d given hi, and we sum up these values, right? So first, the probability of d given hi is 1, and the probability of hi is 1 divided by absolute value of the hypothesis space. And similarly, when the data is inconsistent, the probability of d of hi becomes 0, and probability of hi is still 1 divided by uh, hypothesis space h, right? And ultimately the value that we get is Virgin space itself, right? Virgin space for h with respect to d, right? The ratio of Virgin space as well as the hypothesis space. So that is the reason that p of d, that is probability of the training data d, is replaced with this ratio of Virgin space and hypothesis space in this formula here, right? So I hope that clarifies the aspect of why do we have the P of D as that value. Right. So having been discussed this, let us summarize briefly what is this Bayes theorem implies. Right. So Bayes theorem, what it does, it implies that the posterior probability. I have I'm again repeating this thing, that it implies that the posterior probability, which is P of H given D, probability of the hypothesis given data, under our assumed, this is very important, this is we have assumed, right? This is on the basis of the three assumptions that we have taken. So the Bayes theorem implies that the posterior probability P of H given D under our assumed P of H and P of D given H, then the posterior probability P of H given D is equal to this value, that is the ratio of 1 is to the Virgin space if the data is consistent with the D. Otherwise, it will be 0. So this is a simple summarization of what if I have to say for the Bayesian learning. Right. So a little background about what was the evolution of posterior probability. Right. How do we have this evolution of posterior probability? So posterior probability, as you can see from the diagram here, the posterior probability increases, right, with the increasing training data. Right. So probability, that the posterior probability P of H given D with increasing training data. So here you have three diagrams you can see, wherein we have first as prior probability, which is initial probability. Then we have probability of H given D1, and then we have probability of H given D1 and D2. Right. So the first diagram here, which is the initial probability P of H given D, right? So as you can see the graph in the plot, that the hypothesis uh, is not the maximum hypothesis, or it is not the highest hypothesis, but it is kind of a consistent, or you can say averaged hypothesis, right? Which is consistent, right? I mean, it is in a range, or you can say it is an uniform. So this particular diagram, it represents that the uniform priors assign equal probability for all the hypotheses, right? So whatever the number of hypotheses that we will be having, it will be assigning the equal probability for each hypothesis, right? Then in the second diagram, you can see that when we compute probability of H given D1, that is uh, for a D1 value, the training data D1 and D2 conjunction, when we see that probability increases like compared to the first one. So it is not the equally assigned probability now. It is more, you can say, more focused or uh, more consistent with some set of hypotheses and not all the hypotheses, right? It is not assigning equal probability for each hypothesis, but instead we have some conjunction there, right? We have some limitations. We have some conjunction of D1 and D2. Then in the third diagram, we can see that the posterior probability, right? This is nothing but our posterior probability, right? So the posterior probability of inconsistent hypothesis, these what we call, right, from here to here, we can call it as inconsistent hypothesis, or maybe for here to here. So these hypotheses are inconsistent hypotheses, and as you can see here, in the posterior probability for these inconsistent hypotheses is zero, right? It has become zero, while the probability of the consistent hypothesis, it increases for the hypothesis remaining in the virgin space, right? So it increases. So that's a brief, understanding of how the evolution of posterior probability is done. Now, coming to the second concept, that is the map hypothesis and consistent learner. The, the important aspect to be learned here is that every consistent learner, right? Now, important term, underline this term, that is consistent learner, right? Not all the learner, not every learner, but every consistent learner outputs a maximum a posteriori hypothesis if only we assume a uniform prior probability, right? Whenever I say uniform prior probability, immediately that diagram should come in front of you. That, let me show you that again. This particular diagram, right? It is the assignment of equal probability, that is nothing but uniform probability for each hypothesis. So in map hypothesis and consistent learner, every consistent learner will result into a maximum a posteriori hypothesis, right? But if we assume a uniform prior probability distribution, right? A uniform prior probability distribution over the H, which is the hypothesis space H. That is nothing but that P of Hi is equal to P of Hj for all I and j, right? And only if we assume deterministic and noise-free data. This is very important because these are the assumptions that we have already considered. So only when we assume that it is deterministic and noisy-free training data, that is P of D given H is 1, which is consistent. In other words, the data training data D and hypothesis H are consistent, and it will be 0 otherwise, right? If it is consistent, it will be 1. If it is not consistent, it will be 0. So just to put it into a nutshell again, for the maximum a posteriori hypothesis and the consistent learner, it is very important here that to understand that every consistent learner outputs a maximum a posteriori hypothesis if we assume that we have a uniform prior probability distribution, right? And also we have to assume that we have noisy free as well as deterministic data, that is consistent if the probability is 1, and if it is inconsistent the probability is 0. So this is all about the base theorem and the concept learning, right? So the further topics we'll be discussing in the next lecture, but you have any doubt with respect to what we have discussed today, the session is open for question answer. you have any queries, you can ask. Let it be any silly one, because as and when we proceed, the topics will get more advanced. So if you're carrying forwarding your doubts, you are just simply piling up all the doubts, right? And you might end up not understanding what we are going to discuss in the next class. If you have any doubt with respect to what we have discussed, uh, you can ask those doubt. Let it be any silly one. Anybody with any kind of doubt? Yeah, please answer, guys. If you have any doubt, please ask. If you don't have a doubt, please let me know. Michael says no doubt. What about others? Others, if you have doubt, please ask. I can understand there are few terms which are a little complicated to understand, right? Will not be that will be easy enough to be understood at the first go. But when you have a look on these videos when they are uploaded on YouTube, you can rewind it wherever you want. I'll make the PPTs available once we complete this module, so you can revisit those slides. You can pause the YouTube video when you play this video. You can pause it, take a screenshot of the PowerPoint slides, or make a note of these, right? So only then you will understand when you do it 2 3 times. When you try to understand 2 3 times, only then it will go into your head, because these are not usual terms that we usually see compared to other subjects, right? These are little technical words used with some concepts in from different subjects. So you need to have a brush up of those subjects as well, right? For example, you will not understand what we are discussing here if your probability concepts are not clear, right? So if you have to understand the topics here that we are discussing with respect to Bayesian learning and Bayes theorem, different concept learning, then for that the probability is the fundamentals of the probability is very essential, right? So have a look upon these basic fundamentals also, so that you will grasp the things more faster, right? So if you have still any doubt, you can go through the lecture once again when it is uploaded, and probably your doubts will be clear, right? Because I have touched upon all the basic things, and it should clear all your doubts. There shouldn't be any doubt. But still, if you have any doubt, you can feel free to ask me anytime. Right. So with this, we will stop the today's lecture. You are free to leave the meeting room. Thank you.
Sir, 0 to present, sir.
Yes, Aditya, you are present.
Thank you, sir.
69 presents, sir.
Yes, you have put it in the chat box, right? I have seen in the chat box.